All right, welcome. In this video, I'm going to be working some examples of AP Precalculus free response question number 2. So we're going to be modeling a non-periodic context using the graphing calculator. And I know you saw me go through this in the lesson video, but just in case you didn't, I just want to remind you that we're going to be given a real-life situation with a little bit of data, 2 data points. We're going to use or possibly 3 in the event that it's a quadratic model. In part A, we're going to construct a function model by building a system of equations and probably using a regression. Then in part B, we're going to calculate, apply, and reason with average rates of change and their units. And then in part C, we're going to talk about the assumptions or limitations of that model. Okay, so let's just jump in and look at a few of these examples. So the first one's talking about the height of a tree. So this Chinese bamboo tree exhibits a unique growth pattern where it doesn't really burst through the ground for quite a few years, but once it does, it really starts growing, at least for a while. There's going to be limitations to this model. I think the first important thing to notice is what type of model they're getting at. And so that's h of t equals a times b to the t. That's an exponential model. Okay, and then we're going to pull out the 2 data points. So the first thing I see is after 1 week, the height of the bamboo tree is 3. So I'm going to look at that and say, all right, that means that h of 1 equals 3. And then the next one is at t equals 5, the bamboo tree is 89 feet tall. So I'm going to say h of 5 equals 89. And so when we go to do we're going to be setting up a system of equations and then constructing a function model. So A1, use the given data to write 2 equations that can be used to find the values for constants a and b in the expression for h. Well, we're just going to plug in our value of h and our value of t into that equation. Okay, so for the first data point, h of 1 equals 3, the value of h, the output of the function, is 3, and that's going to be equal to a times b to the t power, where t is equal to 1. And so I'm going to have 3 equals a times b to the 1. And then for my second data point, I'm going to have h of 5 equals 89. So that's going to be 89 equaling a times b to the 5. And then that's all we got, 2 equations that could be used to find the values of constants a and b. And I recognize in this class we have actually gone by hand and divided the second equation by the first and seen that b to the 4 equals 89 over 3. We could take the 4th root and proceed without a calculator. But we've got a calculator, so we might as well use it, right? So I'm going to go into my calculator and I'm going to run an exponential regression. So I'm going to go to the stat menu, edit the lists. My input values are t equals 1 and t equals 5. And then my output values corresponding to those are 3 and 89. Okay. And since there's only 2 unknowns, we only need 2 data points to fit an exponential regression. So we're going to calculate exponential regression. Okay, list 1, list 2, no frequency list, this isn't stats. Okay, with storing the regression equation, I don't think that's going to be necessary with this free response question. If it is, then I'll go back and do it again and make sure it's stored. Okay, so now I've got my values of a and b, so I'm just going to report those, right? That's all we need to do. A equals 1.285, and b is going to equal 2.334. Remember, always 3 decimals in AP Precalculus. Now, for part B, we're going to use the given data that h of 1 equals 3 and h of 5 equals 89 to find the average rate of change of the height of the bamboo tree in feet per week between t equals 1 and t equals 5 weeks. And we're going to express our answer as a decimal approximation, and we're going to show the computations that lead to our answer. All right, so average rate of change, that's slope between 2 points, that's rise over run. So if it's going to be average rate of change of h, it's going to be a fraction, and the numerator is going to be h of 5 minus h of 1, the rise in h, the rise in height of the tree, over the run in time, so divided by 5 and minus 1. Okay, and then we're going to need to actually get the values of h5 and h1. Okay, we're going to say that's 89 minus 3 over 5 minus 1. And whereas usually I would suggest that you just go for a fraction bar in your calculator and, type it in exactly as you see it, I think this is one that we can do, 89 minus 3 is 86, divided by 5 minus 1 is 4, and we can get 21.5. Okay, and that's B1. Okay, part 2 is we're going to interpret the meaning of this answer in the context of the problem. Okay, and so that's where we're going to want to use the units, feet per week, that they gave us to help guide us in the meaning. 21.5 feet per week. That sounds like, oh, that's how much the tree is growing, right? Actively growing, that rate of change. So I'm going to say, it's an average rate of change, so I'm going to start with on average. Okay, what's changing? H. The h means, and that's the in the context of the problem, the height of the tree. That's really important. And since I've got a positive rate of change, I'm going to say it's increasing by 21.5 feet per week. And I think that's going to be good enough because they said in the statement of the question t equals 1 to t equals 5 weeks. But I'm going to just, give the best possible answer, and I'm going to, identify the time interval as well. So I'm going to say on average, the height of the tree increases 21.5 feet per week for t between 1 and 5 weeks. And then for B3, we're going to consider the average rates of change of h from t equals 5 to t equals p weeks, where p is beyond 5. And then we'll ask if those rates of change are greater than or less than the average rates of change from h from 1 to 5 that we found was 21.5. Okay, so I've shown you the graph of what I think h of t looks like. It's exponential growth, right? And it's probably not exactly drawn to scale, but I need to draw it like this in order for you to see what's going on. The average rate of change that we found, that 21.5, that represents the slope of the line that connects those 2 points. So I'm just going to draw in a line right there. Okay, but then I need to think about t equals p, where p is beyond 5. So I'm just going to, for part 3, I'm going to label p out there somewhere. Now that may be a little bit too far to the right, but as long as it's to the right of 5, we're good. And I'm just going to label some point to the right of 5 on the graph, and I'm going to think about the average rate of change from t equals 5 to t equals p. And that'll be the slope of the line that connects the t equals 5 point to the t equals p point. And so I'm going to, drawing that line right there, and I'm going to see it's steeper. Okay, so it's steeper means its average rate of change is greater, right, because it's a greater slope of that line. And I'm going to say, all right, well, I'm going to clearly answer the question first. They ask, are the average rates of change of h between 5 and p greater than or less than the average rates of change from 1 to 5? Well, that's greater. I've got a steeper slope. So I'm going to clearly answer the question, greater. And then I'm going to give my reason after that. I'm going to explain my reasoning. Really, I feel like the reason is the fact that it's exponential growth, or the graph is concave up. So I'm going to say, all right, how do I know it's concave up? Because I'm seeing exponential growth. And how do I know it's exponential growth? Well, h of t equals a times b to the t, and a is a positive number and b is bigger than 1. That's something that we've learned in this class. That guarantees exponential growth. So I'm going to point that out. So a is greater than 0 and b is greater than 1. And so as a result, I've got a graph that's concave up. So I'm going to say the graph of h is concave up, and therefore the rates of change are increasing, because that's what it means to be concave up, is you've got an increasing rate of change. So I would say, and rates of change are increasing, and that would make sense. That would give you a greater rate later on. Okay, so that's part B. All right, now part C, and these are the parts that I feel like I struggle with the most, because I'm not really sure what you're supposed to say. But I mean, I know what the right answer is going to be, but it's that in the context of the problem that gives me a little bit of pause. So for which t value, t equals 4 or t equals 11, should we be more confident in when using the model H? Okay, clearly t equals 4, because that's in between the 2 data points, right? And t equals 11 is well outside of the 2 data points. And so I'm going to say, well, I'm going to clearly answer the question first. T equals 4. Okay. I think the issue with exponential models in general is that they just keep growing at an increasing rate forever, and so they end up kind of ridiculous, with the output values, especially when, we've got some sort of, like, we're living in a finite world, which we definitely are. So I'm going to actually predict the value of h at t equals 11. And so I'm going to go back into the calculator. I'm going to calculate another exponential regression, but this time I'm going to store it into y1. And so I think maybe I will do that just in case I want to do something like this with a question in the future. But as you'll see, part C isn't always just like this or that. Okay, so we've got that. We've stored it into y1. I'm going to quit out and call for y1 of 11. And I'm going to see if that's some ridiculous number of feet. 14,381 feet. Yes, I like this. T equals 4. My reason in the context of the problem is that the model predicts a height of 14,381.134 feet at time t equals 11 months. And, there's about 5,000 feet in a mile. This is almost 3 miles tall. No plant is 3 miles tall. Okay, so I'm going to say, I'm just not going to, editorialize too much on that. I'm going to say that which is not realistic. And I really like that better than you, because, like, interpolation is better than extrapolation. First of all, is not a principle that's really, seen in the course description. Also, it's said in the context of the problem, so it needs to be like, has to do with heights of trees. So I like the idea of plugging in t equals 11, seeing this is not a reasonable answer. Right, the second example I've got for you is going to be, here, let me clear out my calculator. So, what was that? Got number of cars in the parking lot of a local store, and that number of cars is going up then down, so we're going to want to do a quadratic regression. That's something I've seen quite a bit lately when we're studying modeling. All right, yeah, sure enough, L of t is at squared plus bt plus c. All right, that's my quadratic model. So a1, we're going to write equations, but this time it'll be 3 equations because there's 3 data points. So I'm going to write down my data points. H of 0 equals 4. H of 5 equals 21, and H of 8 equals 14. And because there's 3 unknowns in my model, I'm going to need to have 3 data points in order to get a reasonable model. So, all right, what am I thinking? Okay, 3 equations. H of 0 is 4. So 4 equals A times 0 squared, t squared, plus B times t plus c. So that is showing me that c equals 4. Right? So I'd better get 4 as my value of c later on. H of 5 equals 21. So when t equals 5, h equals 21. So, don't think about it too hard. Just plug in the values of L, or not h. Whoops, pardon me, I was still stuck in the height of the bamboo tree. Number of cars in the parking lot, so L, L, L. Okay, so the value of L versus the value of t, there we go. And then value of L is 14 when t equals 8, so a times 8 squared plus b times 8 plus c. Now, this looks like actually the type of system that, I may have shown you how to solve last year in Algebra 2 if you're in my class. 3x3 system, we could do it by hand, we could use a matrix in the calculator, but for us, 3 points, there's only one unique parabola that goes through 3 points, so I should be able to just, type this in and say, okay, 0, 5, and 8 are my input values, 4, 21, whoops, and 14 are my output values, and then I'm going to calculate a quadratic regression, that's option 5, and then I am going to store the regression equation because I ended up wishing I had last time. That didn't go like I wanted. Okay, calculate 5. There we go. Come on, there we go. Y1. And then we're going to calculate, and there we go. So A2, I'm going to say, all right, it looks to me like A is negative 0.717. B is going to equal 6.983. And C is going to equal 4 like I expected. Okay, so that's good. All right, in part B, we're going to gear up to do some average rate of change work. So in B1, we're going to need to find the average rate of change in the number of cars in the parking lot and cars per hour between 5 and 8, and then we're going to do exactly like we did before. All right, so I'm looking for that average rate of change between 5 and 8 to be L of 8 minus L of 5 divided by 8 minus 5. And then that's going to be equal to 14 minus 21 divided by 8 minus 5. Okay, and I know that you've probably got that arithmetic down, but I just want to, model the behavior I would hope to see from y'all in the event that it was more difficult than that. Call for a fraction bar. Type it in right. 14 minus 21 over 8 minus 5 There we go. That's -7/3. Now it asks for that as a decimal approximation. And if you're frustrated with your calculator, well, just go to math and then tell it, I didn't like that, give that to me as a decimal. So that's going to be -2.333. And they gave me the units, so that's going to be cars per hour. All right, I've got a negative average rate of change, so that means that my function is decreasing. So when I go to do part 2, I would say on average, because it's an average rate of change, what does L represent? The number of cars in the lot. Okay, I've got a negative rate of change. You could say is changing by -2.333 cars per hour. We can say it's decreasing by 2.333 cars per hour. What we can't say is decreasing by -2.333 cars per hour, because we're decreasing by a negative number. Like, don't get into that. I'm just going to say, is changing, and I think I'm going to adapt my response on this one. For future problems, I'm going to always go with is changing. At a rate of -2.333 cars per hour for t in the time interval, what was it, 5 to 8 hours. Okay, and then B3, oh wait, whoops, that's too many dots. Okay, B3, the average rate of change found in part 1 can be used to estimate the number of cars in the parking lot, T for T greater than 8 hours. Will these estimates found using... Oh, wait. That, I didn't even read number 2. They did not ask for the interpretation. They asked me to do something completely different. Pardon me, that was a huge mistake. But, that statement is still true. That's just an answer to a different question. All right, to estimate the number of cars in the parking lot at time t equals 7 hours. Okay, so I'm going to say that the number at 7 is going to be approximately equal to the number that there was at 5. So that would be 21 plus the average rate of change, so -2.333 cars per hour, times the number of hours that had elapsed between t equals 5 and t equals 7, right? Okay, 2 hours had passed, so I would expect us to have lost 4.666 cars. And, well, it asked us to estimate the number of cars, and it didn't say round to the nearest whole number. So what I'm going to do is I'm going to go over here, plus 2 times, maybe I'll go and grab that number, that seems more exact, and see, okay, get 49 over 3, okay, which maybe I should ask for a decimal again. That does not seem like the type of thing that's going to be a whole number. That's going to be 16.33 cars. Okay, great, sure. Use the average rates of change found in 1 can be used to estimate the number of cars in the parking lot like we did for t beyond 8 hours. Okay, I think this is again a situation where I'm going to need to draw you a picture. Now, scrolling back, I did see that B was 6.983, which is a little bit less than 7. So the vertex of this parabola is going to be at a little less than 3.5. Now, we did find that A was a negative number, so this is going to be a downward-facing parabola. I'm going to need to sketch the graph here. So I'm going to just give myself something that looks kind of parabola-ish. And I'm going to say this is about t equals 3.5. So t equals 5 to t equals 8 is going to go over there. Okay? And like we saw last time, t equals 5 to t equals 8, that average rate of change represents the slope of the line that connects these 2 points. Now I am going to move this one a little bit so that it goes right through those points. That looks a little bit better. Okay, and what we did really when we found this 16.333 number is we just found, if I can here, allow myself to O, but if I zoom in on it too much, it's going to, not like that. I found something in there. right? We found a point on the line. That's really what we did. So going over here to looking beyond t equals 8 hours, will these estimates, which I'm gonna just found using the average rate of change, well, that would be like something out here or out here, right? Those are times beyond t equals 8. Will they be greater than, less than, or greater than the number of cars predicted by the model? Explain my reasoning. And I really struggle with this because, like, really the reasoning, the proper justification is going to involve calculus. Okay, but this is not a calculus class. So first, I'm going to clearly answer the question. Those estimates will be greater than the true amount because the true amount is, or not even the true amount predicted by the model L. Yeah, okay, so L is the parabola. Average rate of change is the red line. And so, yeah, they will be greater than the number of cars predicted by model L, which who knows how many actually are in there. So I'm going to say greater. Really, again, it has to do with the concavity. Because the graph is concave down, the secant line, that red line, is going to sit above the curve, at least on the outsides. And this whole reasoning with the secant line is really not something we do in calculus very often. I'm going to say because A is negative, that's what is causing it to be concave down. The graph of L is concave down. And the secant line sits above the curve. And the greater comes from the above. But I'm not really sure what else to say besides that, and so I'm just going to leave that one there. All right, now the next one's talking about a rumor that began to spread around a school after Mr. Passwater missed a day. And I can relate to that. And, while I'm at it, just big thanks to Mr. Passwater for providing all these problems free of charge. It's really generous of you. I don't actually know you, but I do appreciate your problem writing skills. And so, moved to Japan, okay. Initially, 7 students knew about the rumor, because they were the ones that started it. After t equals 2, a total of 15 students had heard the rumor. So I'm going to say that, okay, R of 2 equals 15. That's one of my data points. And then my other data point is going to be R of 6 equals 67. Okay, and then the total number of students that have heard the rumor can be modeled by this piecewise model, which is going to be interesting. 7 times a to the t over 2, and negative 213.29 plus b log t. Okay, so what we're going to need to do, this one's going to be a little bit different. We're going to use the data to write 2 equations. I think we'll just be able to solve each equation separately, okay, because a and b are so separate. But I'm going to go here and say, all right, I'm just working below the problem on this one. I don't have those nice rule lines to guide me, but it'll be all right. Okay, so for A1, use the given data to write 2 equations. So t equals 2 belongs to that, part of the domain. So I'm going to use, I'm going to plug in t equals 2 onto that equation. So 7 times a to the 2 over 2 is going to equal r of 2, which is 15. Okay, so 7 times a is 15. I'll be able to solve that. Okay, and then for b, or the other data point, negative 213.29 plus b natural log of t was 6, that's going to equal 67. And I'm going to use that part of the piecewise function because when t equals 6, that is where t is greater than or equal to 6. Okay, so it should work. And I'm going to go over here and say, all right, well, 7a equals 15. That means a equals 15 over 7. But they wanted decimal approximations, so I'm going to go over here and say, all right, to my calculator, I need you to do 15 divided by 7, and I'll get 2.143. And then b, I'm going to have to solve this equation using the calculator. And it's been a while since we've needed to solve the calculator. The unknown right here, that's variable b. Okay, and so I'm going to say, all right, that's what I'm solving for. I don't want to really type b into the calculator. I'm going to just use x. So in the y equals menu, I'm going to clear out whatever regression I've done before. Negative, and we do need to use that negative button, 213.29 plus x times the natural log of 6. And we want to know where that equals 67. We could go down here and type in 67 in y2, but I don't really like the sound of that because then I'd have to change the window to, have a height of 67 at least, or probably more like 70 so I could see the intersection. I'm going to subtract 67 and see where that equals 0, right? Because this stuff here, that's the left side of the equation, that's the right side. Well, they'd be equal when they subtracted and equaled 0. So I'm going to say, well, I'm just going to go with the standard window and hope for the best. Okay, and see, maybe I get a 0 in there. Okay, it's not looking promising. Okay, so I'm going to need some more t values. I cannot imagine that b is going to be a negative number because that would cause the number of students who heard the rumor to decrease. So I'm going to change the window to be something like 0 to 100. And I'm going to change this x scale to 10, and hopefully that'll allow me to see a 0. If not, then I'm going to rethink what I've typed in. Okay, what's going on here? Right, honestly, I'm not sure what's going on here, but I'm thinking about what I would want you to do in this situation. Like, I can't figure it out using the calculator. We're going to need to solve by hand. So I don't know if maybe it's just a little bit bigger than 100 or something, but I'm going to go in on this equation and I'm going to start doing some algebra. Because it's like, what else am I going to do? I'm going to add the 67 to the 213.29, and I'm going to have b times the natural log of 6 is going to equal 67 plus the 213.29. And then I could solve for b by dividing both sides by natural log of 6. Okay, and this, we do need to be careful with the calculator. If we're adding and then dividing, it's kind of a PEMDAS situation. That's not what I wanted. But no, I'm going to quit out of that because I'm going to check my answer later. That was not very smart. Calling for a fraction bar, I'm going to say 67 plus 213.9 divided by the natural log of 6. That's going to be 156.773. Okay, so I'm going to report that over here, 156.773, but I want to verify that using the graph. So I'm going to go from 0 to 160, maybe 180, so it's nice and on the graph with a scale of 10. That should still be fine. And with any luck, we will be seeing a graph coming through. There it is. And then we're going to calculate that 0, give it a left bound of 150 and a right bound of 160. Yep, it looks like it's right in there, 156.43. Wait, what? 0.433. Wait a second. 156.773. 213.9. Is that the right number? 213.29 x log of 6 and 67. 213.29. Okay, yeah, so I definitely did type that in wrong. 29. And then there we get that same number. Okay, well, that's good. I checked my answer, I guess. Because otherwise I would have been sad. I'd had the wrong answer. I would not have earned the point. All right, so 433. And, maybe now would be a good time for me to go and look at the kind of the scoring notes for this one. All right, yes, I did not think to do this when I did the lesson, but this is the equivalent one for modeling a non-periodic context from the course description. And you can see that it's 1 point for having the correct equations and 1 point for having both values of a and b correct, and there is no half point. So we need to have those right. Okay, and that's why it's worth checking our answer. Okay, so back to the original problem set. That's part A. I think we're ready to move on. So part B is going to be about an average rate of change. We already know that going in. Part B1, we're going to compute an average rate of change. So from t equals 2 to t equals 6. So that'll be 67 minus 15 over 6 minus 2 is going to equal, I'm going to use the calculator for that. So I will call for a fraction bar, 67 minus 15 divided by 4, and that's going to give me 13. And, okay, in students per hour. Okay, and then that's, I guess, a decimal approximation, not necessary in that case. Interpret the meaning of the answer from part 1 in the context of the problem. That's where I'm going to start out with on average. Okay, the R represents number of students who have heard the rumor. The number of students who have heard the rumor is changing. I'm changing my approach. By positive 13 students per hour. Between t equals 2 and t equals 6 hours. All right, and then there's a B3. All right, well, B3, I'll just put that in here. Notice what I am not doing is squeezing my answers to these questions amidst the questions themselves. That is sloppy, and I will not give you credit for the homework if you do that. I'm very sorry, but that's not something we do in AP Precalculus. We don't just see a bunch of text and jam in a bunch of work in there, or at least not in my class. Okay, so don't be handing in the homework with it all crammed in like that and expecting to get full credit. That's not going to happen. All right, that's not good practice. It's about the quality, not the quantity. So consider the values that result from the average rate of change, using the average rate of change to estimate the number of students who have heard the rumor, time p between 0 and 6. Okay, going back to the model, 0 to 6 was an exponential model. It was 7 times a was 2.143 to the t over 2. That's an exponential growth curve. And so, I'm going to say from 0 to 6, I've got exponential growth, right? And it stops there, right? Because there's some other function type, it was log. So it would probably be, that's very clever, Mr. Passwater. Okay, that looks a lot like a logistic curve, which is actually what would model a spread of a rumor, or spread of an infectious disease, or something like that. It switches from concave up to concave down halfway through. Very, very clever. I see what you've done there. And are those okay? So we're going to be using the average rate of change. So once again, it's the secant line, the line that connects these 2 points. And I find it interesting that in this free response question, there's such an emphasis on the secant line. That's not really part of the course anywhere else. Or maybe I just missed that, and I should have been showing that to y'all when we were doing the rates of change thing at the beginning of the year. But, we were all new to AP Pre-Cal at that point. That was the first month, so you might understand why that would happen. Is these estimates that we would get from the secant line greater than or less than okay, so that's model R. And then this is what we would get from the average rate of change model, basically a linear model, and that's going to be greater. Okay, so I'm going to make sure, okay, are these estimates less than or greater than the number of students predicted by model R at time t equals p? Well, I'm going to say greater, and my reasoning is once again going to have to do with the concavity of the graph. Okay, on the time interval 0 to 6, R of t is exponential growth. Okay, I know that because a is greater than 0 and... Oh, wait, yeah, I'm going to be... Because a is meaning something else in this question, I'm going to say 7 is greater than 0 and a is greater than 1. Okay, that's a place where we need to be careful. 7 greater than 0 and a is greater than 1. Okay, therefore, graph of r is concave up and secant line sits over the curve. Okay, and I just realized I was partially writing in a place where you couldn't see. I'm very, very zoomed in here. I know what I need to do. I'm just going to take all of this handwriting here and shrink it. I hope don't also grab the text. All right, so the model R is valid on the time interval 0 to 12 hours. Explain how the range of the values of the function R should be limited by the context of the problem. Okay, so it's got to be the output values are... Okay, my best thought on this one, not totally sure what we were going for on this one, but what was valid for range values? I think what this is getting at, the range values, is the number of students who have heard the rumor. And there's obviously an upper limit on the number of students that could possibly have heard the rumor, right? First of all, there's only so many students at the school. And second of all, there's only so many humans on Earth to have heard this rumor at all, right? I'm not a student at that school, but I've heard the rumor now. There's a limited number of people in the school and on the Earth, and so that's why the range values should be limited by the context of the problem. I don't know what we're saying about 0 to 12. I'm gonna plug in 12 and just see what I get. I didn't store this, but negative 213.29 plus, we found b to be 156.433, natural log of 12, right? Yeah, t equals 12. And we get 175. Maybe there's only 175 students in the school or something. I'm not really sure what to say about that. I'm just going to give the best crack I can at it. Should be limited by the context of the problem. There are a limited number of students in the school. And, the maximum number of students that could have heard the rumor at the school would be all of them. And I don't know, if it's me, and I always talk about in calculus, if this is me and it's my AP exam, I'm going to give a little bit more detail. But for pre-calculus, I think, the free response is not, it's so under our control that this 2C, that might be kind of a wild card, and we'll just accept that and know that the work we've done throughout the year to prepare ourselves for multiple choice is actually probably going to be what makes the difference in us getting the credit for this class or not getting the credit. All right, so I'm going to move on to number 4. I believe that's our last one, right? Yeah. Okay, so now, I don't know, I think this was one of our teachers switched this around because it's talking about Mr. Passwater later, but then it's just an athlete at the beginning. Either way, we've got this weightlifting program. We've got B of T, which is a log model, and I kind of remember this one's got something weird going on with like a capital A. Yeah, exactly. So I'm going to just be really clear that B is the log model. Okay, so, and I might need that later on. Now, the given data was at t equals 0 to 20. So b of 0 equals 220. And then at t equals 8, b is equal to 270. Right, so we're going to write two equations that can be used to find the values of a and b. So a1 is going to be, all right, a plus b log of t plus 1. So, wait, b of t, which was 220. Okay, can't really see all of that. Maybe I zoom out a little bit. 220 equals a plus b times the natural log of 0 plus 1. And then b of 8 is equal to 270 equals a plus b natural log of 8 plus 1 is 9. Now, we were intentional about this t plus 1 because that's a little bit weird. You could do a log regression and make the substitution x equals t plus 1. Get your, type in basically 1 and 9 into the x column for your lists, and I'll show you that would give you the same thing. I definitely did that in the lesson video, but for me, I recommend in this case natural log of 1. You need to know that's 0 for this course. Okay, you also have a calculator. So that means that a equals 220. Okay, because 220 equals a plus b times 0, which is, okay, the b times 0 is going to go away, so 220 equals a. And then for b, I'm going to need to find that using a calculator. So 270 equals 220 plus b times the natural log of 9. Well, that means that 50, if I subtract 220 from both sides, equals b times the natural log of 9, and b would equal 50 divided by the log of 9, and I can do that on the calculator as well. 50 divided by, let's see, natural log of 9, and that's going to equal 22.776. Okay, and there we go. Now, if you wanted to do it the other way, with a regression, you would not need any of this business. And so we would say, all right, we're going for y equals a plus b natural log x, where x equals t plus 1, right? Because that's the type of model we can get from the calculator. So I'm going to, in my table, I'm going to eventually be putting x and y being x equals t plus 1, x equals t plus 1, y equals b of t. So 220 and 270. If I go to the calculator to do that, edit the lists, okay, 1 and 9, we'll give that a little delete. 220, 270, delete that one, and then we're going to stat calculate a natural log regression, which is option 9. Okay, I don't think I'm going to store that regression equation because there's something a little bit off with that t plus 1 thing, but there you go. I think that's interesting that the log regression didn't quite give me the exact value 776. Let me once again make sure I typed that in right, because that's 756. Whoops. 756, sure enough, I just copied it down wrong. Okay, so that would be, again, a situation where checking my answer with the second technique would be kind of helpful to make sure I didn't do something wrong and lose that point. Okay, there we go. So I should get the same thing, especially because there was only 2 data points. All right, so then that's where we're going to get that. But I would leave that type of model, you can do it however you want. I'm just going to stop there. Just do what you're going to do. That's the values of A and B. Now we're going to move on to part B. Use the given data to find the average rate of Mr. Passwater's maximum bench press in pounds per week between t equals 2 and t equals 9. We can do that. So that would be B of 8 minus B of 0 divided by 8 minus 0. Okay, so that's going to be 50 divided by 8. I think that's something that we can kind of maybe not do the division mentally, but do the subtractions mentally. And that's going to be 6.25 pounds per week. Okay, B2 is going to ask us for an interpretation in the context of the question. That's going to be, on average, what does B represent? B of T is their maximum bench press. Okay, the maximum bench press is changing by positive 6.25 pounds per week for T in the time interval 0 to 8 weeks, in the first 8 weeks of measuring. Okay, and then B3, let A of T be the estimate of the maximum bench press in pounds using the average rate of change. Okay, so A of T is going to be that secant line thing that I keep graphing in red. Okay, it is known that A of 12 equals this. Compute the residual, okay, given by the model for 12. Do we actually know because that's what I don't understand. It's like residual is actual minus predicted. Is there any sort of information about T equals 12 that I've read past? Estimates. Okay, I just, like, what I don't understand is which one's actual, right? Because residual is actual minus predicted, and all right, I'm just going to assume that the actual is B from the model because the residual of this estimate, so this estimate is going to be the prediction. So A of 12 is the prediction. That's my interpretation of this question. I don't know about this one. So residual is actual minus predicted. Okay, and so we're going to say the actual is going to be B of 12 minus, let's see, 217.665, or no, 65. Lots of 2 decimal numbers in this homework. All right, so B of 12, I've got, it's A plus B natural log of, there it is, 12 was natural log of 2. All right, and 276.547. Oh, but wait, that's my B of 12, and then I'm going to take the answer and subtract 217.65, and I'm going to get 58.896. Now, it was talking about a negative residual. Okay, so must have been that the actual amount that he was able to bench press was the opposite. That's okay. I'm going to say 277.65. And I copied it wrong. Okay, maybe I should go and try that again. No, okay, I was right. Okay, minus 277.65. Okay, I'm just not typing in the numbers right today. And so let me just see if I can, yeah, there we go. And we can change that to a 77. And that's going to be negative 1.103. Okay, and that's the residual for that prediction. And the residuals will always be negative. Okay, well, I think that must have to do with the concavity, right? Because that seems to be always the thing. A plus B natural log of T plus 1. All right, that is a log function increases at a decreasing rate provided that everything is positive. So that's kind of what I've got. All right, that looks nice enough. And so, yeah, the residual will be the actual, which is B. So this is the log curve. That's B of T. And then predicted is going to be A of T, which is something we would get using the average rate of change, which is represented by the secant line. So this is going to be, let's see if I want it to go through perfectly. That looks really nice. And then I'm going to call that A of T. And so residual is actual minus predicted. So actual minus predicted. Okay, man, how residuals of the estimates will always be negative. Explain why this is true. Residual less than 0 because the graph of b of t is concave down, and the secant line sits above the curve for t beyond that second point, which was t greater than 8. And for t greater than 9, yeah, that will be negative. Okay, yeah. There we go. Part C is decides he should use model B to make predictions about his maximum bench press beyond 12 weeks as long as the difference between model B and model A does not exceed 20 pounds. How many weeks should he use model B? Give a reason for your answer. Okay, well, that's going to involve some pretty serious calculator work. And so I'm going to get all of this stuff and shrink it down by quite a bit. Yeah. So what I need to do is get an equation for model A. And that's something that I have not done yet. So what I'm going to do is I'm going to say, all right, for part C, A of t, we can use either of the 2 points that we have. Really, it's a line. So, oh man, how do I want to do this? I hadn't considered this as a possibility. It's a line that goes through those 2 points. You know, you can see that the y-intercept is going to be 220 because b of 0 equals 220. Yeah, I might say 220 plus the average rate of change times t. So it's plus 6.25 t. Now, you could have done 270 plus 6.25 times t minus 8 because you started off at t equals 8. It's going to end up with the same curve. I'm not sure. What I'm going to do is I'm going to say, all right, a of t in y1. Maybe I'll put it in y2 because that's red. 220 plus 6.25 t. Okay, I thought maybe if I hit the X button that would work, but I don't know what button on my keyboard corresponds to that one. B of t, I've got that. That's 220 plus, okay, what was the actual value though? It was 50 over the natural log of 9. Okay, pardon my vanity, I just want this to be super exact. Okay, 50 over the natural log of 9. Right, yeah, and that was how I got that other value, yeah, okay. Times natural log of t plus 1. Okay, now what I'm going to do, a plus b log t plus 1, yeah. Okay, I'm going to actually turn off the graphing of these two things, and I'm going to say that it was talking about the difference between the actual and the predicted does not exceed 20. Let me think, which one was greater? A was greater. So I'm going to do y3 equals y2 minus y1. And I'm realizing that I have not, for anybody that's working with a TI-83, I have not modeled how to find y1 in this video. It's in variables, y variables, function mode. Okay, there's the list of y's, y2 minus y1. That's what I'm going to be graphing, and I am going to need to change the window. So I need to go beyond 12 weeks. I don't think I need to go to 180 weeks. Let's go to 60 weeks. And then the y max should be, like, we're looking for where it hits 20, so maybe I'll go up to 30 and see what I'm looking at with this graph. See how that goes. Okay, there we go. Yeah. We see the black curve is increasing, and so I'm going to tell it to go ahead and stop graphing. Okay, we can generally do that by acting like we're turning the calculator off. There we go. And then we can go over here and change the window. I don't need 0 to 60. Let's make that 0 to 30. And then we're going to also need to graph 20 so we can calculate that intersection. All right. So hopefully this doesn't take quite as long to graph. But that's really all we're waiting for on this one. This one was a little tricky. I've definitely spent more than my budgeted 15 minutes on this problem, I think. Okay, we're just waiting for it to graph. I definitely should cut the window down smaller, but okay, calculate an intersection between the black curve and the pink curve. Give it a guess. And we'll get 12.740. I think 12.7, so for 3/4 of a week beyond that, I don't know. I might have typed something in wrong. I'm just going to go with it because I'm so far into I mean, like, it's just one problem. I would say 12.740, because that's when, because I use the calculator to solve an equation, that's where a of t minus b of t equals 20. At least according to what I think I got on the calculator. But I'm done with this problem set. That was a good set of examples of free response question 2 of varying difficulties and, types. So that's all for this video. Thanks for watching.